So both Priya and Feryal are experts, professors, theoreticians of black holes. This is really, for all three of us, actually, really central to all of our work in very different ways. And it's the kind of situation where each of us has such a different focus, despite that we all work on black holes, that we have a lot to learn from each other. So I think this is going to be really fun. I mean, if we were sitting on a couch together, we'd be able to ask each other a lot of questions, and that's kind of what we're going to do tonight. So I wanted to show some of these visuals. I'll try to distinguish what are animations and what are real simulations. So this is an animation. It is not an actual observation.
Should I duck a bit?
What was that?
Should I duck so that?
Yeah, you should duck. No, it's okay. So this is sort of a classic visualization of a black hole. So I just wanted to start in the beginning. What is a black hole? We all have these sort of ways of explaining them. Feryal, what do you usually say when somebody asks you, what is a black hole?
So I say it's a dense object. It's the densest object that we know in the universe. Mm-hmm. We know of several types. There are some that form from dead stars when they run out of fuel, and there are some that are huge. They are at the centers of galaxies, and they formed over basically the lifetime of the universe.
So one of the things is when people say they're enormous, they're actually physically small.
Right,
so
exactly.
That's a really big misunderstanding that I run into a lot. I mean, a black hole is physically incredibly small in distance.
Yeah, so the way you make something dense is you take a lot of stuff, mass, and you squeeze it into something very, very small. So the actual volume they take up is tiny, but there's just so much mass in there. Like, we're talking about, for some black holes, 10 billion times the mass of our sun. And it's in a tiny, tiny center of a galaxy.
So if it was a black hole the mass of the sun, how big would it be?
It would be about 3 kilometers if you had to squeeze all the matter in the sun to make it have the idea here, right, is what the compactness really does. It tells you how intense the gravity is going to be. So how much of an influence it's going to exert on objects right around it.
So if we took the sun, or you had an evil genius who figured out a way to collapse the sun to a black hole, it would fit in Manhattan.
Oh, absolutely.
Yeah.
Oh, much smaller. Yeah.
Yeah, it would fit in Central Park.
Yeah.
Yeah, about, right?
Yeah.
I mean,
we're
2
very
miles.
New York centric. Yeah. So I guess one of the things I would want to ask is, how did this discovery happen? Like, why are they so bizarre? So they're very dense, but why are they dark? Right? This is the classic conundrum and kind of the history of it. Priya, I know you've thought in your book a lot about the history of science in general, but of black holes.
I mean, I think these are incredibly enigmatic objects, partly because of these totally bizarre sort of properties they have, so density and how tightly they're packed and how intense their gravity is. But also they're kind of interesting because they were discovered not as real objects in the universe. The history is that they were found as a mathematical solution, an exact solution to Einstein's field equations that actually describe all of space and time and the evolution of everything in the universe.
And Einstein didn't believe it.
Yeah,
Famously.
Einstein. Yeah, and he thought that the field equations were so complex that there wouldn't be an exact solution. And lo and behold, a few months after he presented the theory in 1915, Carl Schwarzschild found a solution. So I think one of the reasons that historically, as a scientific idea, black holes are very interesting because they started out as a merely mathematical entity with bizarre properties, and the correspondence to real objects in the universe took a very long time to establish.
Right, so Schwarzschild, I mean, one of the great anecdotes is that he was allegedly and maybe apocryphally calculating ballistic trajectories during the war, World War I, while he's on the Russian front.
I think that's true, yeah.
Yeah, it is true, but I don't think it was actually in the trenches, but I like that part.
Yeah,
throw
I like
in
that
there.
part too.
It's good, because when my graduate students can't get any work done, I'm like, are you in the goddamn trenches of World War I? Calculating like ballistic trajectories? So he's like reading the proceedings of the Prussian Academy of Sciences, as you do, right?
While you're at war.
Right, while you're at war, and he says something to Einstein. They were friends, I guess. I hadn't really realized that until recently. And he said something like, I've had the pleasure to wander through the land of your ideas, And very quickly, comes up with a solution. Einstein believes a solution, but Feryal,
Oh, yeah.
why doesn't he believe that they're physically real?
So they didn't think that things that dense and so dense that they would actually lose their surface and collapse into a singularity, so something infinitely dense, would actually happen in the real universe. So of course he believed the math, and it's a very simple, very elegant solution. And funny enough, it's not just Einstein, but Sir Arthur Eddington too, one of the pioneer figures of general relativity. So Einstein's theory, the first experimental verification, he didn't believe it either.
Yeah.
So
I mean,
they were.
It's hard to believe.
It is hard to
I
believe.
can't crush this clicker. You know, it's not
Yeah.
easy to crush things. Atomic
Yeah.
forces resist
Yeah.
collapse. So it's sensible, actually, to think that it would be impossible.
Yeah, exactly.
So-
You go through layers of crushing before you can get to, oh, wait, there is no force that can stop this anymore. And it's just going to keep on collapsing into this infinite
Do
density.
you think that if there's a mathematical solution, that nature will always figure out a way to do it?
No, I don't.
Not always.
I do.
I don't.
There's a multiverse. I mean, anything can happen.
I mean, if
But
I
I thought you said, when you said nature, you meant, I thought, an instantiation here that we could go measure or see.
Well, okay, so let's talk about that. Let's talk about how did it happen that you go from Einstein's very reasonable response, which is that this is beautiful math, I'll help you get this published, but nature will protect us from their formation, to actually theorizing before they're observed, like Oppenheimer, theorizing, again, very involved with the war effort, that it would happen. Like, how do you get to that point? But we should maybe talk about collapse in a second. But isn't it kind of fascinating that nature did find a way? And what was the way exactly?
Right. I think what is really fascinating is how, from this mathematical solution, with simulations that were done during World War II for other reasons, understanding detonations, there was a realization that you could have explosions that looked like the end states of stars that could then eventually give you a multiplicity of fates. So if you have a very massive star, then you could end up with an object that looks rather like a black hole, that keeps crushing down. You're left with a very dense, compact object. Whereas if you start out with a star that is not as massive,
Our sun?
like our sun, you would get a completely different fate. So you would get, a neutron star, you would get a white dwarf at the end of stellar evolution. So this sort of, this tussle between gravity and the energy of fusion that keeps the centers of stars going, it's sort of that tussle, and when gravity wins that tussle, and that was what the equations showed them when they were able to actually compute them in great precision. They were able to see that there is a point where gravity basically takes over. And as Feryal mentioned, at that point, it's a point of no return. There's no other force that can actually withstand the crushing of gravity.
So it is kind of fascinating. They're studying nuclear physics because they're in a race for the nuclear weaponry. And the same equations that they're used to understand nuclear physics are so amoral, right, that they also apply to this super abstract concept of the emergence of stars and their lives and deaths. And so it's really linked to the war effort that they made the discoveries. I mean, Oppenheimer's first paper was published in 1939, right, during the the Nazi advance on Poland, and it was kind of lost in obscurity.
Right.
So,
Interestingly, he got the neutron star solution wrong, They calculated what could hold up a neutron star, so black holes, one step before a black hole forms. So it still has a surface, but it's not the form of matter that we are familiar with on Earth. And they asked what could hold up such a star, and they got that part wrong.
Mm-hmm.
So they said, oh, neutron stars wouldn't exist in nature. This is the Oppenheimer-Volkoff paper.
do you think it's okay to get things wrong occasionally?
Oh, it's fun to get things wrong. I mean,
My first failed cosmology made me so happy when I realized I was wrong. I thought we lived inside the sphere of the Earth.
All right, when you were trying to figure out the topology.
Yeah, I was
right?
so excited when I learned we lived on the surface of the Earth. It was like way more interesting than my idea. So
Yeah,
tell me
but-
why they're black, why black holes are dark.
So The classic way we explain it is that when gravity is so strong, it pulls everything towards it. And because light has mass, it also pulls light towards it. So basically, as you're headed towards a black hole, if you're far away, there are exits you can take if you're oriented in the right way. But as you get closer and closer, especially to that part that's called the event horizon, that distance, then there is nothing you can do. You can't run backwards. And light can't run backwards, even at the speed that it goes in. So that part becomes like an infinite vacuum. Everything can go in, but nothing can come out. So, and it just looks black.
I think about it slightly differently. And sort of, if you think of, when we are launching rockets from the surface of the Earth, for example, right? You sort of have to launch them at about 11 sort of kilometers per second. It's like 30 times the speed of sound. That's why we need rockets, right, to boost. And so you can think of the black hole as a kind of entity from which the escape speed to actually launch something off is greater than the speed of light. So that sort of automatically shows you that not even light can escape, and therefore they'll be dark.
So here we have, again, this is an animation. It's not real. We've never taken a picture of a black hole. It's important that people know that. Well, okay, we'll get there. Nobody's ever released the press report.
No, that's certainly true.
A direct image.
Which they will any minute now. But so this was a visualization of the black hole basically casting a shadow. I mean, that's effectively what it does, right? It casts a shadow on the sky because any light that comes near it falls in. And why does it look so smeary, Priya, like this?
Right, so, when you think about the fate of light rays that graze close to sort of the sacred boundary of the event horizon, what happens is that some of these light rays that will cross basically are lost. There are some that are going to skirt and they're sort of going to be in Dante's limbo forever, right? And that's sort of the photon ring, so that's sort of what you see. And then there's stuff, because of the intense bending of light, because the shape of space is so dramatically modified right around the black hole, that you can see, if you will, the back of your head. So you see the sort of smearing when you see the sort of the top where you see the...
So if you were standing at the right location and you had a flashlight, and the light from the flashlight took an orbit, it could bounce off the back of your head and come back to your eyes, and you'd look at the back of your head. I've always wanted to get a better image of the back of my hair. Like aligning
Sounds
the
a little
mirrors.
complicated, right?
I could use it as a method to like check my hair before going on stage.
Yeah, it is a way to see things behind you. Like actually that outer circle that you see, it's called the Einstein ring. It's made up of light that's entirely behind the black hole, and it's what we call gravitationally lensed, basically bent towards you. I mean, like the back of your head. So
well, you can't hide behind a black hole. If you're hiding behind a black hole,
you can't hide behind
gets
the black
lensed
hole.
around. So yeah, I always say this, if you're like in a space battle, like don't try to hide behind the black hole. It's like it's not a good spot. So I actually have, this is different than a cartoony animation. This is actually a mathematical model by Andrew Hamilton, who's a physicist in Colorado. So it's a completely mathematical simulation of what it would be like if you were an astronaut and you were orbiting a black hole. And so the reason why the ring is swirling is really because of your own orbit, right? So you're seeing our own galaxy behind the black hole being lensed. Now, we were talking about it as an object, and I kind of wanted to take issue with that. So Feryal, you said it's a very dense object, but right here at the event horizon, there's nothing.
Right. I mean, so
it's actually empty.
So that's what it's a singularity.
Well,
but
not
I
yet.
don't want to start with, it's an infinite singularity. No. So, yeah, technically that's true. It doesn't have a surface. It's not really an object the way we know other objects.
Yeah, so if you walked into the shadow of the event horizon, what would you experience?
Actually, not much.
Not much.
So the tidal force would bother you, but otherwise you're just falling in. I mean,
no one can hear you scream.
No,
well, not even light can escape, right?
Exactly.
So there you are.
Yeah. And yeah, no one can see if your hair is being torn apart either, so you'll be fine.
Good.
Yeah. So
I'll have one consolation. Yeah,
right.
as I fall in.
Exactly.
So also time would slow down, right? For you, time would slow down.
But you wouldn't experience.
You wouldn't experience it, but your friend, your poor friend who was waiting outside for you.
So Priya, are waiting for me for coffee somewhere back at the Earth, and I'm falling through the event horizon. It could be like several million years.
Yeah,
before.
yeah, we would think that not much is happening to you. You're kind of frozen in that horizon, and you're like, "What are you talking about? I'm going straight in."
And you're going really fast. You're evolving
Yeah.
really quickly.
Yeah.
So these are two myths that I love to dispel. One is that black holes are objects. They're actually nothing. They're sort of regions of space. They're places as much as anything. And also that, black holes are dark. They're only dark from the outside.
That's right.
They can be very bright on the inside. So how does that happen?
Well, I mean, this simulation actually shows that, right? I mean, you're starting to see light coming from all areas. I mean, all directions of the black hole here.
Yeah, so you're inside the black. This, I think, astronaut in this simulation is already inside the black hole. And so they're collecting light from the whole galaxy. So for them, it's remarkably bright for the microsecond they have to live. Right? So the only thing we do know for sure is like death by black hole is assured, right?
Absolutely.
Right, exactly.
So
But I think a lot of the intriguing questions, though, Janna, right? They still remain. Like we don't really understand. We can talk about simulate what's going to happen to an astronaut or whatever, but we also know that when you go into a black hole, it's unclear what's happening to the information about the properties of the person who's falling into the black hole, right? Do you lose that information? As you know, right? That's much debated right now. And there's a really nice analogy that I think is sort of fun to think about. And, it's not mine, it's Stephen Hawking's, which is, if you think of an Encyclopedia Britannica, right? And you want to look up the capital of India, and it's New Delhi, you look it up. Then you put the Encyclopedia Britannica in a box, and then you burn it, right? And all the ashes are in that box. Nothing's left the box, right? So in principle, the information that New Delhi is the capital of India is still in there, just that we don't know how it's stored anymore, and we don't know how to retrieve it either, right? I mean, we know when it is the encyclopedia that it's printed paper, blah, 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 but so I think this is a big raging question, by the way. Like, how is this information actually stored? And how can it, if at all, can it be retrieved? I think, and people have gone back and forth on it, right, Janna? I mean, Stephen himself thought that...
Stephen would make many bets saying that the information was lost. Then he would concede the bets. Then people would tell him, why did you concede? You conceded too early. So, yeah, it's been going back and forth since 1974, probably.
So it's kind of messy what happens when you fall into
it is this...
So
please.
I would say it is actually one of the controversies surrounding black holes, what happens to information that Priya was talking about. In fact, we've been talking about this point of no return, the event horizon. There are also a lot of people who work on general relativity that argue that that horizon is not there. So the singularity, that infinite density at the center forms, but the horizon never forms. And we call that the naked singularity, as you know.
Yeah.
So things would look differently if there was a naked singularity versus a horizon.
Well,
and on top of that, even if there is a horizon, and we know there is also quantum mechanics going on there, how does it look? Does the information get stored on the skin, and it is in principle retrievable, even if we don't know how to? Or does it truly get lost? I mean, I would say that's one of the main controversies.
So in the context of what we're describing, just to orient people about the difference between the event horizon and the singularity, we have, this is again just a simulation, just a cartoon of a stellar explosion, of a supernova explosion. So this was the work that Oppenheimer and Wheeler were doing, where they understood that stars were basically thermonuclear bombs, and that at the end of the life cycle of a heavy enough star, it would explode, and the core that remained, if that was big enough, it would collapse under its own weight. And then the idea was that when it collapsed small enough, so here you might have something 10 times the mass of the sun and 60 kilometers across, that's really small. When it collapses, it forms the event horizon, right? So the event horizon, like you were saying, Priya, is when light can't escape, but then what happens to the material of the star? What happens to it?
It's still energy, and we don't know in what form.
But it doesn't stay at the surface anymore. The
doesn't
event
stay at the
horizon
surface
isn't the
anymore.
surface of a thing.
No.
So it just keeps falling.
It keeps falling.
It keeps falling. See, the event horizon's almost like an archaeological fossil left behind in some sense. And then it
Yeah.
keeps falling, and then we don't know.
That's
It
right.
could be crushed down. We say that, oh, a black hole 10 times the mass of the sun is 60 kilometers across, but the matter that formed it might be what?
Tiny, in a very,
Like the
very
size
long
of a grain of sand.
Yeah, absolutely.
And that's
Yeah.
the singularity.
That's
so the
the
singularity
singularity.
is different
Yeah.
than this big shadow.
Yeah.
Yeah,
And-
indeed. I mean, the event horizon is not marked with a flag saying, now you have arrived at the event horizon. I mean, as we were saying, to somebody falling in, they wouldn't know.
It might be like stepping in the shadow of a tree. Just
Yeah.
totally benign.
They don't know that they've
But I
passed
think
the event horizon.
But the peculiar thing about the black hole is this kind of combination, this kind of boundary that then encloses the singularity. And the fact that the singularity is a real annoying thing because all known laws of physics kind of break down in our trying to understand what's going on there, right? So at some level, I mean, if one wants to be poetic, right, it's sort of the limits of our knowledge, basically. It's sort of, you can think of this of the event horizon that's encasing the singularity as kind of, you know, the boundary between knowability and unknowability in a way, right? It's sort of,
It protects us from whatever's inside there.
yeah.
So because no information can leave the black hole, because nothing can travel faster than the speed of light, could we know from the outside the difference between there being a singularity or there being a new universe blowing out from the singularity or there being a quantum remnant? Can we know, or does that, like you say, that boundary of knowledge mean we're forever on the other side of that
Well, I
information?
think mathematically, you can come up with solutions that will help you figure out the structure right around the singularity. So mathematically, you can postulate that what the singularity does is port you onto another universe, right? To another region of space-time entirely, from which we are causally disconnected, right?
Our future cannot be affected by what's inside the
Inside
black
the
hole. It's over.
Yeah.
We can affect it,
Right.
but it can't affect us.
Yeah.
Yeah, and it depends also a little bit on how different that object is, how big those fluctuations are. One of the things that we're working on right now, we being the community, is can we find observational signatures that something turned truly into a black hole in the sense that we understand it here, like Einstein's theory sense, or something else, like there are quantum fluctuations at the horizon scale, or it's a naked singularity. So, you know, they can look different in appearance or in how fast the signals take to travel around it. So if we saw some periodic phenomenon, for example, but it depends very much on how big those differences are.
So let's talk about what we can see, because we've described them as massive but spatially small. So this is animation just showing how tiny they are, right? In the scheme of the galaxy, if that's our Milky Way, it's a little marble at several thousand light years distance. We will never be able to see such a thing. Never. I mean, a stellar mass black hole. We'll talk
Right,
about the
right,
other ones.
right.
So, I mean, it's kind of an extraordinary, even Oppenheimer and Wheeler, who coined the term black hole in the 60s, thought,
So it has a darker history.
oh yes, tell us that, it's
Yeah,
good.
so in the 1700s, the term originated, black hole originated, well before there was any idea of these objects. And it turns out that it's the name of an infamous prison in India where the local Nawab imprisoned the mercenary soldiers from the East India Company and left them overnight. Basically, they didn't make it out. So it was a point of no return. And so it became sort of used in vernacular, and then later in the 60s, Wheeler used that term. So it was the black hole of Calcutta, really. And that was what he repurposed to
So
describe
I heard
black
the
holes.
story differently. Maybe we have to merge our histories. You know, what did they say? History is very difficult to predict.
Right.
But what I heard was that Wheeler was giving a lecture where he kept saying the endpoint of complete gravitational collapse, which he got tired of saying repeatedly. And I heard it was above Tom's Restaurant on Broadway by Columbia, where the Goddard Space Center is now. And apparently someone shouted from the background, how about black hole? Now, I don't know.
I think Marsha Bertusiak claims that.
Okay,
Right. Yeah,
but
definitely.
you don't believe it? Maybe the person shouting it out was referring to the black hole of Calcutta.
Well, the black hole of Calcutta, I mean, was a thing because, it's there in Mason and Dixon, in Pichon. It's there in Edgar Allan Poe's poetry. So, that term has sort of been around.
So we keep throwing the name Wheeler around. John Wheeler was the great American relativist, student of Einstein's theory, who really trained the first generation of relativists. Richard Feynman, Kip Thorne, who just recently won the Nobel Prize. So many people were trained by Wheeler in general relativity. And so he was this incredibly formative figure in the history of this subject.
I mean, and a subject which was considered very esoteric and mathematical till really the late 60s, when we started finding these objects that appeared to be powered by growing black holes, quasars.
Right, so this is crazy to actually have this as another animation. If black holes are so tiny, so dark, a little shadow, dark against a dark sky, why would we have any insane aspiration to actually see them? Feryal,
So before the stuff around the black hole gets to this event horizon and is no longer part of our observable universe, they actually become really hot really fast. The speed with which they circle the black hole becomes very high. And when that happens, they give out copious amounts of light. And anywhere from radio wavelengths, the meter-long wavelengths, to X-rays to gamma rays. So we have a lot of different ways of understanding as matter is, for example, a star losing its envelope, or just gas clouds, or whatever happens to be in the path. As it's falling into the black hole and feeding it, it becomes very, very luminous.
Right.
And it's that infalling part on its way to the black hole that we are able to
The
observe.
dying gasps of matter.
The dying gasps. Yeah. But
so, like in that previous cartoon, it's like eating the neighboring star like it's cotton candy, right? It's just pulling out tufts of the star.
Because its gravity is so strong that it's not going to let anything just wander by, like it is going to attract it towards itself. And if it has a little bit of a swirl, then it's going to make this, what we call the accretion disk. It's just going to make its way down this toilet bowl. And in the meantime, luckily, it's just going to give out a lot of light that we can study and learn about black holes.
And you mentioned quasars, Priya, which are...
Yeah, so we believe that quasars are some of the brightest objects in the universe. They're sort of cosmic lighthouses, and we believe they're so bright because they really are objects which are feeding very, very rapidly. So these sort of feasting black holes where a lot of matter is siphoning in. And, and we're talking about matter at the rate of 10% of the mass of our sun gobbled per second, right? So that's a really huge feeding rate. And that glows very, very brightly, and we see these cosmic beacons out to very large distances in the universe. They sort of almost out to when the universe was a very small fraction of its current age. And so these objects, the amount of energy that you get out of them, they're so bright that the only way we think they can be powered, just by doing the physics and the math and the numbers, is that they have to be powered by accretion. In fact, Donald Lynden Bell at Cambridge was the one who figured out that from the energetics, from the amount of energy, that it had to be matter flowing into a black hole. And it turns out then you can work out how big the black hole has to be such a good sucker, right? And it turns out that they have to be supermassive. That's just a technical word for something that has to be well above 1 million times the mass of our sun. And, and we thought, lo and behold, right, that these are sort of rare objects, they're very bright. But it turns out that when black holes are not feasting, they're fasting, like the one in the center of our galaxy and most other nearby galaxies. When they're not feeding, they're still there, sitting, maybe feeding at a very low rate. So they're not going to sort of blaze like a quasar. They're going to be this little piddly thing sitting in there. But their intense gravity is still sensed by the stars right around the black hole.
Mm-hmm. So here we have this history of a mathematical solution, nuclear physics, exploding dead stars. how do you get from 10 times the mass of the sun, maybe even 20 or 30 times the mass of the sun, to 1 million or 1 billion? I mean, wasn't that a huge surprise?
So earlier in the universe, the stars may have been more massive, and the clusters that they formed may have been more massive than what we're seeing today. And that helps a little bit in the sense that you can then form slightly bigger black holes to begin with.
Are they formed through stellar collapse, are you saying?
Either collapse of individual stars or collapse of entire star clusters. We don't know the answer to that.
And I have a pet idea.
I know you have a pet.
Everybody has a pet idea, and we can.
Priya's hoping to test her pet idea.
Yeah, we are, right? With the next generation of X-ray telescope and James Webb Space Telescope, we are trying to see where these first black holes formed and how big they are. They were.
Right. But it must have been for the people who first discovered quasars. Okay, the energetics, as you're saying, Priya, mathematically, you would think, oh, wow, the only thing that could really do that would be a gravitational object, incredibly dense, et cetera. But the numerology works out nicely, but physical origin was mind-blowing.
Oh, absolutely. And I think that, you know that the end states of stars, as you just showed in that really nice animation, so you have this explosion, you're left with a little black hole, right? So the pathway from going from there to something that's 1 million times, 4 million times the mass of the sun, that's in the center of our own galaxy, there's a lot of overfeeding that needs to be happening, for such a hole to be, black hole to grow. So we believe that one possibility is that you have episodes of overfeeding, or you can start out making black holes really obese from the get-go. So instead of forming a little piddly black hole, that's the end state of the lifetime of a massive star, maybe what you can do is have an entire early galaxy before it forms stars, when it's all gassy, kind of siphon in gas driven by some sort of instability, like when you pull the plug in your bathtub and the water goes in a vortex really fast. Something akin to that with the gas in the very early universe. Then you can make these seeds that are 10,000 times, 100,000 times the mass of the sun, then growing it by, 10 times, 20 times.
How do you grow it by 10 or 20 times? Collisions with supermassives?
Before we talk about that, let me just say, either way it's difficult, right? I mean, this is a truly unsolved problem. If you start with something, even if you say, okay, the stars were more massive, maybe there were clusters of them, I'm starting out with something 100 or 1,000 times the mass of the sun, you have to feed it a lot. Because in 700-800 million years, which sounds a lot to us, but it's really not much in the beginning of the universe, they're already at 1 billion times the mass of the sun.
These are the quasars,
These
the bright quasars.
The brightest things that we saw at very high redshifts, meaning early in the universe. So that is difficult. And what Priya is describing, the alternative, so get them obese from the get-go, like just make a healthy baby and then you don't have to grow it as much. That's also difficult because things like to just break up. We call it fragmentation, right? I mean, one of the reasons why we don't have very massive stars right now is because they just break up as they're forming. All I'm saying is it's an unsolved problem.
These are open questions, right? So we're waiting for data from upcoming X-ray telescopes.
Let's emphasize how populous they are, right? It's not like, oh, there are a few quasars out there, there are these obscure rare objects we're trying to explain. Yeah. We think that there are supermassive black holes in essentially, more or less, every galaxy in the universe. So that's hundreds of billions of galaxies just in the region we can see.
Right.
And so each one of them seems to have a supermassive black hole.
Right. The brightest, most massive ones might be rare. But, if it's not 10 billion or 1 billion times the mass of the sun, it's still there. It's a little bit smaller.
And there's a family, right? There's a whole, if you take our galaxy, you have one that's a few million times in the center. But then it's littered with black holes, smaller black holes, the end states of all the stars, right? Generations of stars that have formed. Yeah. So they are galaxies are basically littered with black holes, tiny black holes, intermediate mass black holes, and the supermassive that manages to sit down in the center. I think what has been intriguing, though, wouldn't you say, in the last decade or so, is that the mass of the black hole, the supermassive one, oomphy as it is in the center, right, it's still tiny compared to the mass of the stars in a galaxy. It's a millionth of the mass of all the stars. But now we believe and we understand that these little black holes sitting there during their feasting and fasting actually shape the entire properties of galaxies over cosmic time. They are sort of like pistons that turn on and off star formation. They seem to do a lot. They have like outsized influence.
How do they like turn star formation on and off? Like, so star formation, you're saying, if I can connect the dots, is crucial to understanding the world in which we live because we need to live on a star of a particular size. Our sun is, modest. We don't have to have too many stars near us, so we're not under chaotic conditions, and we have this
it's
kind of
the
nice...
DNA of the universe.
Sorry?
It's the DNA of the universe,
Yes.
star formation.
Right, so we have this nice habitable, lovely little planet on the wings of the Milky Way galaxy, a safe 27 light years from the supermassive black hole. And you're saying effectively that to have those conditions for habitability and life might actually be traceable back to the supermassive black hole.
I think the chain from life is kind of a long set of ifs and chains there. But what we do know, for galaxies to look the way that they do now, to have the kind of star formation, the ages of stars, where the stars are located in a galaxy, the distribution.
What
black
their
holes
shape is, are there ellipses, are there spirals like our own? That must have something to do with the black hole.
Believe.
So what, like the black hole powering quasars and jets regulates
So it heats up the
densities
gas.
It heats up the gas and it blows some stuff out. It can
Right.
regulate
It
the size of the
rearranges
galaxy.
matter. It rearranges matter, even though it occupies a tiny, tiny place. It rearranges matter in galaxies out to very, very large scales. We know that now. We see evidence for jets. And so on. But we also know that what is critical for star formation is you need cold clumps of gas to get denser and denser, and then they eventually light up and form stars. So any process that prevents cooling, that prevents star formation, that injects energy and heat, like the black holes do, is going to scupper star formation. So we believe that there are these sort of regulated cycles.
Yeah, so Janna, you were asking how do we know that there are black holes if they are dark? And we were talking about how bright the gas gets and how energetic the gas gets en route to the black hole. Well, it basically blasts radiation and, just winds, powerful jets and winds to the surrounding gas. And so we think that it forms a self-regulating cycle. So a lot of matter will fall in, it will create this very energetic environment where it's just blasting the surroundings with light and jets and whatever. So that will stop the gas from coming in, it will stop star formation, and then it will quiet down and then start all over again.
Right. There are people like me who also believe that this is also, part of the story, is the way a black hole will also eventually stunt its own growth. Because what it will do, it will evacuate all the gas that feeds it, right? So the hand that feeds has been cut off now. And so we believe that all of these processes are intricate. They are sort of, they dovetail with each other. And that is the explanation for many sort of correlations we see between the properties of black holes and the galaxies that they inhabit.
There must be a reason everyone has a black hole at its core. It can't just be, right? So I guess it's one of these hierarchical questions. Did the black hole come before the galaxy? Did the galaxy get shaped by the black hole? But Feryal, I'm wondering if you would go as far to say that you can't imagine a planetary system or a solar system like ours were it not for the black hole.
I am not sure about that. Clearly the way that histories of galaxies happened were shaped by black holes. But could it have happened in some other way? So once you form the black hole, explaining why it's at the center of the galaxy is pretty easy because it's the most massive thing and it will just gravitationally fall to the center.
Sure.
And then we're talking about how influential it is to its surroundings and how it can go through many, many cycles, affecting how much star formation happens, etc. And during all of this, actually, one of the things that's happening is stars are forming heavy metals in their bellies, and through those supernova explosions that you were talking about, and we talked about Oppenheimer, etc., they're returning it back into the galaxy. So they're enriching it with even oxygen and carbon and everything else, let alone, more massive or higher elements in the periodic table. So that cycle is absolutely necessary to form planetary systems.
But I think, Janna, I would actually put myself out there to say that, you probably need a fasting black hole in order a quiet one in the center of a galaxy to enable planetary systems to survive and enable them to eventually, after, there are many ifs, right, in this sort of the so-called Drake equation of, all the factors that, to give you life, and then intelligent life, sentient life.
Sure.
Blah, blah. Yeah.
But our supermassive black hole, Sagestar, which we'll talk about actually in a second, is essentially quiescent.
Absolutely.
Yeah.
Essentially.
Sagestar is
So it was
quiescent.
probably a quasar. There's probably another galaxy 5 billion light years away.
It was probably a quasar in ages ago.
Right, so there's a galaxy 5 billion light years away that's looking at us, seeing it when it was a quasar.
That's right.
That's right. That's certainly true. So our own galactic center black hole, which we call Sagestar lovingly.
Because it's in the direction of the constellation Sagittarius.
It is toward, so you can find where the center of our galaxy is by looking for Sagittarius. And that one is kind of wimpy. So I'm wondering if it never had a true quasar phase. I mean, clearly it ate a lot at some point, but not, it's only
You're like criticizing your
4
grandfather here, like-
million. What?
It's like criticizing your ancestors. I don't know.
Yeah.
It's like-
I
Your
mean,
wimpy
I don't know. Maybe
ancestors.
it's just a modest black hole. It said it grew to 4 million times the mass of the sun and kind of stopped there.
So can you tell me about these images, which I took from your work, actually?
Sure. So these are different ways in which our galactic center black hole, Sagittarius A star, might look if we were to take a picture of it. And why is there an uncertainty there? Well, we're talking about swirling gas, we're talking about how it emits light, etc. But as we come closer and closer to the event horizon, we don't know exactly how that gas is being transported into the black hole. So if it remains in a accretion disk, like we were talking about, it would look like something on the left.
So in order to see the shadow, you need a light behind the shadow.
Right.
You need some
you
contrast.
Can only, you can only see a shadow against light.
And I just,
so
I just want to emphasize again, we've never been able to take a picture of any black hole. Like when I show you these animations
A direct
of it,
picture.
a
But we have
direct
indirect,
picture.
indirect
We have
evidence.
indirect, we
No.
collect light, but we've never taken a
We've never-
resolvable picture. So
Yeah.
what would it take? So this black hole, we said, was 4 million times the mass of the sun. It's 27,000 light years away.
Yeah.
And so it's like if you were to move that, it'd be like resolving a piece of fruit on the moon. That's what I often hear.
Well, we like to say a donut because it also should look a little bit like a donut. More like a half-eaten donut because as gas is swirling, the part that's coming towards you is brighter and the part receding from you is dimmer. So that's why it looks like this half crescent on the left rather than a full circle. So this half-eaten donut, if you put it on the moon and try to take a picture with your camera, that's basically the technology that we need. And you would say that's completely crazy. We will never be able to do that. But actually, this is something we've been working on for about 20 years. We have now grown to a collaboration of about 200 people. And what we've done is, since no single telescope, no single dish is going to be big enough, we hooked up different telescopes across the globe in order to have the resolving power to be able to take a picture of Sagittarius
So it's
A star.
basically a telescope the size of the Earth.
Yeah, that's what you're creating, a virtual telescope
And
the size
do
of
you
the
think
Earth.
this will succeed? Priya, do you think this will succeed?
No,
She's
I
on
mean,
the collaboration.
I
We
can't
didn't-
talk
right.
She's
No.
biased.
Yeah, right. No, I was giggling in between because the person who had this crazy idea and has worked tirelessly to make this happen was at MIT with us. He was actually a co-graduate student with Janna, Shep Doleman, right?
So
And
that
I
is
think-
not true, but
Well, that part was true. He was
worked hard.
Yeah, that
He's
he
been
was-
working tirelessly, but the idea doesn't come from him. But that's
Sure,
okay.
sure. But I mean, making the, coming up with the network, putting things together to make the entire Earth be basically one radio dish, one large radio dish, right? He was pretty instrumental in doing that. I think that I'm very optimistic. I think this is the best chance we have. This is the black hole that is nearest to us, and if we can pull this off anywhere in the universe, it's here. And I think we have the technology. We have the capability.
So let me go a step further. In 2017, we took the first, what we call the full array observations, meaning all the telescopes that are critical for this effort were functional. They pointed to not just our galactic center black hole, Sagestar, but also a nearby black hole, M87.
A more massive one.
A more
much more massive
so
one.
farther away, but 1,000 times more massive. So it also looks as big as anything can in the sky. So we have the data. In 2018, we repeated our observing campaign.
We're all waiting for the press release.
I know.
We
I
are.
mean, really.
We're working very hard. So I just took a break to come here, and I'm going to go right back to work.
Get back to work. Okay. So Andromeda also is a nearby galaxy. Which one's Andromeda is? How big is that?
I have
Black
no
hole?
idea.
I feel like it's a billion.
Andromeda, no, it's not. It's less massive. It's about
It's less
10
massive?
times more massive
But
than
the
ours.
galaxy itself is bigger.
Yeah.
And so
The
we're on a
galaxy itself is
collision
bigger.
course with Andromeda, right? We will merge with this. So there's two spiral galaxies. They look like they're frozen in the timescale in which we can perceive it, but over the next
Well, it's the only
few
object
billion
in
years.
the universe that's actually falling towards us,
Right.
right? Everything else in the universe is like moving away.
So in a few billion years, our supermassive black holes will merge.
Yes. Yeah.
And I mean, that's got to be also part of the theory of how they grow. That would
That's
be
right.
a big one.
And I think that, you're right, that, part of the larger picture that we have for how galaxies assemble over cosmic time and cosmic history is it's by collisions of galaxies. So little galaxies form first, then they collide with each other, and all their components collide, right? And we now know that galaxies are primarily made of dark matter, which is this other enigmatic thing. And then we have stars, and you have the black hole in the center. They all kind of crash into each other. And this is one way that we think might also be important in how to build the mass up of black holes, especially early on in the universe. The crash rate is pretty high in the early universe because at later times, the universe is expanding, and it's harder to find things to crash into, for galaxies to find each other to crash into, as it
So
were.
our Milky Way galaxy, which is a collection of 100 billion stars, probably has experienced previous collisions with other galaxies.
Yeah, we think that it has, statistically speaking, so this is sort of work that we do on building models, like possible life histories, right, within this context. And we think that the Milky Way probably had 3 major, on average between 3 to 5 major big-time collisions, many small collisions with things that were much, much smaller than itself.
Well, I could talk about that forever, but I wanted to ask Feryal about the big announcement today. So I don't know if people heard, but the European Southern Observatory, I stole this next animation from them, had a press release early this morning, US time, afternoon in Europe, about observations of Sagestar, this black hole that we're discussing.
Yes, this is another very exciting experiment that's been ongoing. So this is a set of 4 infrared telescopes that are in close proximity. They are located in Chile, and they've been following the stars around that orbit around
So
our
here we're
galactic
honing
center
in
black
to the
hole.
center of our
Yeah.
galaxy.
So this is actual images. I mean, this is not a simulation.
This is not.
Yeah.
Okay, so right now we switch to a simulation.
Yeah.
And that's the donuts that we were talking about, sort of. And so what you're seeing here is the star cluster that is orbiting around the galactic center black hole. And
that's real data. Those ellipses
those
are real tracks of about 27 stars. That
yeah,
we now
so
have.
reconstructed tracks from real data, that's certainly true. And one of them, the S2 star, comes really close to the black hole. So the gravity experiment is what it's called. The set of 4 telescopes has high enough resolution that it was able to follow the track of this S2 star extremely well over a long period of time. So for the first time, it detected a redshift, meaning the wavelength of light that is emitted from the star changed a little bit to the red as it climbed out of the gravitational well of the black hole.
The stretching
to reach
due
us.
to the gravity, basically, of the
Absolutely,
black
gravitational redshift. So, you know, it's orbiting around this black hole, getting really close, and it's emitting light, and that light has to climb out of that gravitational well to reach us on Earth, to reach our telescopes. So it was the detection of the gravitational redshift, that small change in the wavelength of light, that is, first of all, it tells us the mass of the black hole with incredible precision.
And that mass is?
Okay,
You don't have to give me all the decimal points.
yeah, I'm trying to think. Yeah, 4 million times the mass of the sun, but I don't remember how.
So it's 4 million times the mass of the sun, but it probably would fit inside our solar system.
Absolutely.
It wouldn't be
Yeah,
4 million times bigger than our solar system.
Oh, yeah,
It would
yeah.
come out to the radius of one of the outer
So
planets.
it's 12 million kilometers across.
Which is small.
Which is small.
And I
I mean,
think-
it sounds big, but it's small.
And I think the major feat here is that this star came so close to the black hole that this is the point where we can see the most intense gravitational effect of the black hole.
Yeah.
So that's the, you know, the great sort of awesome thing here, that it comes, you know, it's not as close as we would think it would be, right? I mean, it's still
didn't get torn
it's
apart.
about
Close.
say,
Otherwise-
1,500 times the event horizon or something, right? It's like 1,500 times.
Yeah.
So further
So
away.
it didn't get torn apart.
It didn't get torn apart.
didn't get
And it didn't get
Exactly.
swallowed.
It didn't get
no,
swallowed.
So, yes, indeed, it has done this passage before and it survives intact. And at the point of closest approach, which, as Priya is saying, is not even that close, but still, gravity-wise, it's very strong. So
Right.
we can see that redshift. And what this experiment does differently is that they have such sharp eyes that they can follow it and take little spectra as it's going around. So then
Right,
we
and
get
then
the
when
mass.
when you move away from the point of closest contact with the black hole, right, then you see the change. So, and they're able to track it further on as it's moving away.
Yeah.
So we're not seeing the shadow of the black hole. We're not taking a picture of the black hole,
No,
but we're
this is-
watching stuff orbit something dark.
Further out.
Right.
Further out, but it's something dark. It's orbiting something we can't see. It's not luminous. And we assess that the mass of the object must be enormous, 4 million times the mass of the sun from the movement, but we
Yes.
realize it must be very, very spatially small.
That's right.
Yes.
So that's what we
exactly.
mean when we say it's
Right,
a black
and,
hole.
and I
That's what we
think that,
mean.
you know, the kind of picture that we're trying to build up, right? We are trying to build up sort of the Event Horizon Telescope observations are going to tell us about right around the event horizon. And this is for the same black hole at the center of our galaxy, 1,500 times further away. So we've really kind of pinned this guy. Basically, we know where it is. We know how massive it is. So the
Yeah,
question is figuring out what are the impacts of this black hole at various distances. So even 1,500 times or so outside the event horizon, right? The gravity impacts, right? And it's affecting this redshift.
also-
So this is actually, sorry to interrupt.
No, please.
This is great news for the Event Horizon Telescope because one of the reasons we want to take a picture is now coming back full circle. We want to understand if the black holes predicted by Einstein's theory of gravity, general relativity, are actually what we think they are. And in order to do that test, we need to know the mass of the black hole that we're looking at. And the better we know it, the more precise our test is. So this was excellent news for the Event Horizon Telescope too. Now there's no wiggle room, basically. Either that half donut with a shadow in the middle is there and it's as big as predicted by the theory, or it's not.
So I know the headlines were, general relativity tested, confirmed, although as we know that you can never really fully confirm a theory, but tested, confirmed by this experiment. But isn't there a part of you that's a little disappointed? Like, don't we all secretly kind of want to see something that's we're wrong about? It's like you said, we love being wrong.
Yeah,
like
we
being
do,
wrong
we
would be
do.
so exciting if it wasn't coming back over and over again with the theory of
So
relativity.
the reason I wasn't too disappointed with this one is because it tested only one aspect of general relativity, which is the equivalence principle. It doesn't actually tell you how strong the gravity should be. So there is still work to do, don't worry.
So I just want to give us a little global perspective. This is a digital atlas made by the American Museum of Natural History. I like to show it a lot with the Rubin Museum. It's actually placing everything that we know in our galaxy as accurately as it can based on real observations. So this is not a cartoon. Here we're going into our Milky Way galaxy, and you see, if you've ever seen the Milky Way, the reason why it looks like this beautiful riff on the sky is because we're in the galaxy. We see it edge on, and here you're coming to our humble star. You kind of turn off the light on it, and we're coming to our little solar system. And I just want to give a little bit of perspective that we do all of this from that little rock, right? I mean, we've never gone beyond the moon. I mean, going to the moon was extraordinary, but we've never gone beyond the moon, and we do all of this by
Right,
kind
but
of
we managed to
passively-
send Voyager 1 and 2 beyond the
Voyager,
solar
right,
system.
which is
not
amazing.
using- Which is incredible,
So
right?
Voyager,
Yeah.
which was launched in the 70s, when did it go beyond the solar system?
2012, I think Voyager 1 actually crossed the heliopause, and we think Voyager 2 another couple of years
I love
later.
Voyager. Go Voyager!
Yeah, I know.
You know, when Sagan put that golden disc, the record on the, which was a sort of representation of humanity, cultural selection, people were upset that he was indicating where we were located as though aliens were going to find this golden record and then like hunt us down. But it's been, 30 some years, and Voyager is just outside of this. So like if you found the record, you could there we are, we're like right there.
Yes.
So it's not the biggest threat. But this is quite extraordinary. So just to give people a sense of the scale, how many black holes do you think there are in the universe? We've already sort of toyed with this concept, but an assessment of how many black holes there are in the universe.
I think that's a very difficult question. I mean, it's difficult to answer even if you ask how many black holes are in our galaxy.
So let's start with our galaxy. There's one
Okay, so
supermassive.
one big one.
Right, one
we
big
can
one.
agree on that. And we don't think there are any other big ones that we haven't seen.
They could be if they were wandering around. So theoretical work suggests
Sure.
that if you could have another supermassive one, or maybe one that's a slightly lighter cousin, sort of, wandering around in the outskirts of our galaxy where there's not a whole lot of gas, not a whole lot going on, you could accommodate a few. The theoretical work, like our simulations now show us, that you could have a few wanderers.
Now,
It
what
would have
about-
to be smaller. It would have to be far out. Otherwise, it just spirals in and comes to the center of the galaxy and merges with the existing one. So as far as the stellar mass ones, things that are about 5 times the mass of the sun above, we know for a fact that there are 26, I think, is what we're up to right now. In our own galaxy. So when I say a confirmed black hole, what I mean is we have really good data of things orbiting it. It's dark. We can infer the mass.
What we have detected, though, is X-ray radiation from these little black holes, and we found a swarm of them really right around the inner regions. They're pretty faint and pretty challenging
Tens
to
of
find.
thousands, possibly.
Yeah. So again, I'm distinguishing between things that we've done precise measurements on, and that's literally handfuls, and then we can infer through other means, like the swarm around our galactic center, that is in the tens of thousands. And then there must be many more that just don't have a companion, so they are not glowing, and we don't know that they're there.
If we add up all the other galaxies, I think it would be extremely conservative to say 1 trillion in our
Sure, but
observable
I mean,
universe.
I think,
it could be more like
the trillion is impressive. However, they don't punch their weight in terms of the total mass in stars in the universe or dark matter in the universe. They're like a tiny, tiny fraction, much less than 1/100% or something in the overall mass inventory of stuff. So yes, the number, as I said earlier on, I think the universe is probably littered with black holes of all kinds. But but they don't actually contribute significantly to the overall mass inventory, but they have outsized influence.
So let's just, in our last kinds of thoughts, just for the last few minutes, why aren't we falling into the supermassive black hole at the center of our galaxy? Or will we ever? Will we ever is the question.
Sorry, will we ever?
Fall into the supermassive black hole at the center of our galaxy?
No, we're very far away.
Never?
No.
I think unless,
Of course we
are
will.
very, very far away,
I mean,
so we're
Yes,
not
but
going
of
to
course
fall
we
in.
will. We have
could.
to.
I mean, you'd need a very Baroque condition. You'd need
No, you
to
just
engineer.
need gravitational waves.
We
We'll
can
fall
send
in.
you on a one-way trip if you're really interested, but otherwise we're not going there.
So here's the argument,
Okay,
though.
what's your argument?
My
let's
argument
hear
is
your
that, like anything that orbits a black hole, we emit gravitational waves, which is this energy that we give back to space-time, causing ripples in space-time. So our orbit decays, granted incredibly
Oh, come on.
slightly.
It's a very
Yes,
it'll
but this
take
is
an
just-
eternity. It'll take an eternity.
Look, an eternity, no, not an eternity. It'll take a lot longer than the past. The future is a lot
No,
longer
but our
than the
sun
past.
is going to die out in 5.
Sure, I'm not saying are we going to be alive.
Right.
I'm not asking if you and I are going to be having that coffee.
That's right.
But I think it is absolutely a fact that everything in the universe in the far, far future, it's true, it's a number I can't even estimate. Like the universe is 14 billion years old and the future is staggeringly longer than that.
But Janna,
Staggeringly longer than that.
there's a bigger uncertainty, right? Which is this overall stretching of space that dark energy is engendering, right? That if it turns out that the accelerating expansion of the universe, we've seen a glimpse of it. We know that it happens. It kicks in about a few billion years, for in the universe. We know it starts to dominate. But if that really continues relentlessly, then the fate of the universe is different, right?
Sure,
So
I agree with that. So it's not guaranteed if the universe expansion gets more severe or if it doesn't decay. But if it does decay or if it doesn't get incredibly more severe so that we have what you're referring to as a big rip where the galaxy itself gets torn apart, we must, everything that will fall into black holes. That is the ultimate fate of everything in the universe unless it gets ripped apart.
It's contingent on other macro properties of the universe that we don't yet know.
Yeah.
Right? Another unsolved problem.
acceleration.
So I will give you that gravitationally bound objects will remain gravitationally bound even in a big rip scenario, but I don't think they will all fall into a black hole. They will form isolated regions where basically gravitational radiation just doesn't play a role. They're just too far apart.
Little island universes, if you will.
Yeah.
But
I'm
so
voting for islands.
we're not an isolated island universe from our black hole. We orbit it. We are actually in orbit around it. So we are actually definitely emitting gravitational radiation because of our orbit. So our orbit is getting smaller. It just takes us, I don't know, however long to make one orbit, and it's really, really small. But if that's left alone, there is one and only one fate for this solar
Fair
system.
enough,
After
because
the sun
our
blows
galaxy
up,
is like a closed box, if you will, right?
Yeah.
So
Yes.
fair enough. But I
agree.
think the question is, how...
I'm going to get them to relent. But it is true. There could be these other factors like the dark energy and the expansion of the universe. But it is interesting, that's right. You get so isolated that the time scale is so long that you're no longer talking about things you can assess. But it is an interesting, at least possible fate that black holes are the ultimate death state of the entire universe. And here's where I want to get to the really weird stuff, what I call the hard stuff. Oh, that was nothing.
That was nothing.
Which is
Speculate away, Janna.
Suppose we have to get to the stuff we don't know, right? That's the fun
No,
part.
I'm totally for it, and I'm not joking, because I think, look, black holes came out of this whole Einstein's theory, right? One can argue was a creative leap of imagination that he took, right? And then all the stuff that was in the realm of unreal became real, right? So, hey, you never know. You might be coming up with something.
Ahead. I plan on being around to check it out. So let's say we have this very far future of black holes, hypothetically. What then? Is that the end state? Is that really, truly the death state? I mean, you were talking about black hole evaporation. So we are just getting to the idea that black holes are dark, they emit no light, they reflect no light, nothing escapes. And then Hawking comes along and says in this very subtle, very slow...
Chapter 7, Brief History of Time. Remember it so vividly.
Yeah, he realized that quantum mechanics allowed for the possibility, this very subtle possibility, that the black hole would actually evaporate. Now, it's incredibly slow.
It is.
The bigger the black hole, the longer it takes.
So you know what I thought of? Maybe it's a contest between whether Hawking radiation is more efficient or gravitational wave emission is more efficient.
Sure, and that's actually an intriguing question.
We think Hawking radiation must happen. I mean, that in itself isn't that weird.
So basically, the Hawking radiation and evaporation is just the idea that, empty space vacuum is really not empty. It's bustling with particles and antiparticles that are zooming in and out of existence, right? And so if you are right around a black hole, you could imagine a scenario where basically one of this particle-antiparticle pair gets sucked into the black hole. With less energy is extracted, if you will, is lost. The black hole will shrink in its size a little bit, and this other guy, the partner, would actually leave. And so we would detect that, right? Or we would detect these pairs that then become energy, gamma ray radiation, very energetic light that we would see later on. The only problem with this, right, is that any sort of reasonable sized black hole, our friends, the guys we've been talking about, the real guys, the evaporation timescale is just so long.
But remember what she was talking about before, the time it takes
for
gravitational wave emission to fall into the black hole. So
Janna's two eternities may actually kind of fight off each other.
It will be a comparison of two eternities.
Mm-hmm.
That's right.
Well, I love this. I just, I wanted to open it up to a Q&A, but before I do, I just wanted to ask Feryal and then you, Priya, what's the thing you're most excited about on the horizon for your area, your specific area, like your real, like when you go home, what are you going to lose sleep over?
Pun intended or no pun intended on the horizon?
Oh, see what I did there? Not intended, sadly.
I am most excited about the Event Horizon Telescope, and
this is this one where the whole Earth is one telescope.
The whole
looking
Earth is
at
one
the
telescope.
Sagestar.
We have 2 years of data on it, and we are trying to reconstruct the images and analyze them to understand what happens in the horizon.
Yeah, and Priya?
So I'm most excited about the possibility with the James Webb Space Telescope for getting at the origin of the first black holes, to sort of really figure out how the first black holes came to be, and also this whole picture of their growth history, right? But guys, it's like delayed gratification. My patience is being tested as the James Webb deadline is sort of moving along. But I think we're pretty close to ratifying, either validating or invalidating a lot of our conceptions of how black holes form, grow, and evolve over cosmic time. So I think it's super exciting. And I'm excited about the Event Horizon, of course. I'm excited about every black hole discovery. So this morning when I saw this, I was like, oh, wow, this is cool. I hope we get to talk about it.
Excellent, lovely. It's a great note to end on. Let's thank our guests before we open to the Q&A. We're only going to do a few minutes of questions. There are mics running around the room. If you have a mic in your hand, you can just try us. We can't see very well out in the audience if there are questions. Who has a mic?
Hi, can you hear me?
Yeah,
Cool.
Can't see you, but can hear you.
Yeah.
Okay, so my question is, does every star collapse into a black hole? And how does that change how many black holes there are? It seems like, at least in my mind, that there'd be more and more black holes forming. So I'm wondering if it's sort of a consistent number or if that changes over time.
Sure, I can take this. No, not every star forms a black hole. So our sun, for example, is pretty small, and it's going to end its life as a white dwarf. It is going to run out of fuel. It's going to expand at first and then contract, and it's no longer going to generate energy, so it's going to form a dense core, but it's not it's not actually that dense, and the dead form of stars like our sun is going to be a white dwarf. A little bit more massive, so somewhere between maybe 8 times and 20 times the mass of our sun. They are going to still go through this contraction phase, but they're going to go past the white dwarf stage into neutron stars, even denser cores, the ones that are the size of Manhattan, let's say. And anything even more massive than that, when it dies and runs out of fuel, it's going to collapse into a black hole.
Right.
So the number of black holes are growing, yes, because new stars are being formed, they live out their life, they die, they either have a supernova explosion if they're massive enough, or after that.
Yeah, if I may add, when stars are born, they're born with a range of natal birth masses. So that's the thing. So this is a thing called the initial mass function. Stars are born with a range of masses, so each one will live out its life and end its life in one of these 3 fates, basically.
Yeah, the smallest star would be a fraction of the mass of our sun, and the most massive one forming nowadays would be probably 500 times the mass of the sun.
Right, and and there are also going to be some things that form in the universe that just failed to ignite, basically, that failed stars, basically. You have those brown dwarfs, they're also sort of lurking around.
I've heard a number as big as 1% of all the stars in the galaxy will ultimately end up as black holes.
That's about right. If you take
So that's about
where
10
we
billion.
think the mass
about 10
cutoff is, and add up everything that's towards, about
That's
a
10
percent.
billion stars at the end of the day. That's a lot. That's why I was saying it to be a huge number.
That's
10
why
billion
like
it's a
stars.
huge
litters
number.
of black holes.
Right, times 100 billion galaxies, it's actually a huge number, but right, Priya, less than the rest of the stuff. Anyone else have a mic, please?
Yes, I do. And this is a question for you. Something that you mentioned early on in an offhand manner, and I believe I heard you say something about a black hole blowing out a new universe. I'm just wondering if you can clarify if there's significance to
Yeah,
that.
she's the one to ask that one.
So we don't know how to predict what happens when all of the stuff of the star that forms the black hole continues to collapse to basically microscopic scales. So imagine all the material of a star being in a microscopic scale. But one of the conjectures was from some of the very early relativists that you could actually sew together space-times. It's not a prediction. It's just asking, could I
But
make
Janna,
a quilt out of it?
This is, so you're just saying that basically we don't have a quantum level understanding of gravity, right?
We
basically.
don't yet understand quantum gravity. So without quantum gravity, we can't make a prediction. We can't say, oh, I can follow from the initial state to the final state. But you could make a quilt and just ask, does a quilt actually, is it possible to sew the quilt together? And so people have tried mathematically to sew a Big Bang onto the interior of a black hole. And it can be done. So it's, again, it's not a prediction. It's just saying there's some continuity that's conceivable. And what that would mean is that even though the black hole is only, say, the size of Central Park on the outside, it could be as big as an entire universe on the inside. You know, it's like Doctor Who's TARDIS. You know, it's much bigger on the inside than it is on the outside. And that's just one of these extraordinary things that warping space-time allows you to do. A lot of people don't think it's viable for all kinds of complex reasons, but it always recurs, you know, in the imagination.
Yeah, no, and I think you're absolutely right that, you know, that kind of grand unification of gravity with quantum mechanics has remained a pipe dream still, right?
Yeah, and one of the interesting issues that we didn't have a chance to get anywhere near is whether or not we'll discover that gravity is kind of an illusion when we understand quantum gravity, that it's not fundamental and it doesn't exist, but that's a whole other psychon.
Right.
We'll do that another time. Is there another mic out there?
So if I'm understanding this correctly, the black holes are kind of eating everything around it and then emitting energy. So I mean, I might be oversimplifying probably, but is that sort of its purpose? If you could say that black holes had a purpose? To eat the stuff so that it can emit energy?
So I would say stuff is emitting light and energy on its way to the black hole, but once it's in there, other than this minuscule Hawking radiation that we were talking about at the end, it's actually staying in there. So that's just the first part of what you were asking. Do black holes have a purpose?
I don't know. I mean, do cosmic objects have intention? I don't know.
we?
I don't know. but I think that, we think of black holes basically as, one of the sort of triumvirate, the trinity of dark entities in the universe, right? Dark matter, dark energy, and black holes are basically these sort of bizarre entities that don't interact with light in our usual ways. So we can just think of them as, phobic to sort of electromagnetism, if you will, right? So I don't know. I don't think I want to say any more about sort of purpose. Their purpose seems to be that they want to defy interacting with any of the other known forces, right, other than gravity.
Yeah, so I mean, maybe they turn out to be inevitable given our physical laws.
Oh, totally. I think that's quite clear.
I would not call it a purpose, but it's just the way that the physical laws in our universe, and maybe there are many more out there that work differently, work. Black holes turn out to be inevitable, and that's why they are ubiquitous, and that's why they are so interesting and, at the center of many phenomena.
When we do think about quantum stories, we think of black holes as fundamental particles of gravity. And that's
Absolutely.
extraordinary. Like a chair is not a fundamental particle, a neutron star, nothing else in the universe. Except, at that large scale, at the macroscopic scale, except possibly black holes, meaning there was a lot of discussion about whether or not we would actually make them at the Large Hadron Collider when we smashed particles together, that they would be like any other product, a fundamental particle that could be
would just
created,
emerge.
That would just emerge,
right.
and would Hawking evaporate safely away? Fingers
That's
crossed. So there was a lot of concern about whether the Large Hadron Collider was safe.
Right,
Yeah,
but I think...
Well, not a lot. That's not reasonable.
it was hyped.
Because you know how much energy you're putting in, and you know that you can't get out more than you're putting in. So it was a bit of a hype.
It was a bit of a hype.
No, but I think that, coming back to sort of, I think your question was meant to be somewhat philosophical, right? And I think that's where I want to circle back to what Janna said. That, the Big Bang, we believe, was also a singularity, right? It might be a different kind of singularity from the interior of a black hole. We don't know. But, it's sort of, in terms of coming full circle, there's a lot of uncertainty about exactly how this whole thing started, the thing being the entire universe. And similarly, we don't know how things end, right? So
maybe we're inside a black hole. Maybe we're the Big Bang inside the black hole. I think we only have time for one more question. I know it's getting warm in here, and people want to go to the garden and come to the book table outside, but I'd love to grab one more question if someone has the mic.
I was going to ask something about entropy, but more broadly, are there any ways in which black holes have challenged our preconceptions about the universe that we had before studying them, or our predictions that we had about the future? Are there any ways in which black holes have challenged our preconceptions about the universe or our predictions for the way the universe will grow and develop?
So have black holes changed our predictions?
Or challenged?
Or challenged our predictions for I think you said have grown and developed, so the history and future, I'll interpret that as.
I think I might have mentioned this earlier on, right? That we never imagined that they would have this kind of outsized influence given the scales that we've been talking about, even for supermassive black holes in the center of galaxies. They seem to be shaping the overall fate of galaxies via the kind of modulation of star formation in galaxies. This is something that has really changed. We never thought that they would play such an important role in galaxy formation. We just thought they were sort of sitting ducks. They're sort of sitting there, they happen to be there. But it now turns out that they are likely playing a very active role. So that has been sort of one thing that has shifted in the last decade with data.
Oh, I think that's extraordinary, and it is very recent. And you know, when you say past 10 years, that means there's a long buildup of sort of dispute and uncertainty,
Absolutely.
and now it's starting to really
Observations, calculations, yeah, indeed.
And you know, new instruments were needed to, you know, new instruments had to be invented and data had to be taken. And I think Janna and Feryal both kind of alluded to this earlier. One of the interesting things about black holes is that we've gotten a really rich picture of them when we have patched together data from many different wavelengths, right? Many different windows into the universe, including gravitational waves now. So this whole sort of patchwork of the energy that's coming out in visible light, in X-rays, gamma rays, infrared, everything put together is just phenomenal. How much we know now, right?
Yeah, and just I do find it really chilling, this idea that black holes might have sculpted the universe on the largest scales. I mean, that is totally extraordinary and unanticipated from where we started, but the conversation and the history of black holes.
The
And
Are they even
mathematical
real, right?
curiosity, right?
yeah, a mathematical, lovely, but nonetheless mathematical curiosity, you know, and then the elegance of math kind of forcing its way onto nature again. And that does seem to be kind of an extraordinary history of that. So I know I said it was the last question, but I was talking and I can't be the last one to talk. So I'm going to get one more question and then we're out of here.
Hi.
Yeah.
You've talked a lot about black holes in terms of space, matter, and I was wondering, what happens to your perception of time as you approach a black hole, and what happens to your perception of time after the event horizon?
After the event horizon is particularly interesting.
Yeah.
Right.
So, I mean, we believe that what really happens once you cross the event horizon is that the role of space and time actually get flipped. So remember, we talk about this sort of four-dimensional sheet called space-time, which is sort of the way in which we describe everything that happens in the universe, and we need to sort of bring time in there because time is a relative thing that you measure only with respect to something else. And so it takes, you know, light 8 minutes to reach us from the sun, and if the sun shuts off, we won't know for 8 minutes, right? So to take that into account, sort of cosmic distances and the finite speed of light, Einstein realized that time has to be intrinsically combined with space to give you a description of not just the shape of space, but of all motion and of all gravity. So once you cross the event horizon, we believe structurally space and time flip, right?
Yeah.
And so in the mathematical equations, what that means, what do I mean by time and space? Well, mathematical equations, they actually swap where they appear in the
So
equations,
the
right?
singularity is in your future.
Yeah.
It's not at a,
It's
we think
always
of it
in the-
naively
it
as
is
the center of the
center.
black hole,
Oh,
but in
yes.
reality, if you're falling in,
Yeah.
it seems to you like it's your future.
It's your
Yeah.
future.
It's totally inevitable.
It's
as
totally
inevitable
inevitable.
as the next
Yeah.
second is, or the next
Yeah.
second, or the
Yeah,
next
and
second.
in fact, when we were defining black holes, we kind of alluded to that, right? I mean, if you're just passing from a distance, it's fine. You can determine your future. But if you're getting close to the black hole, then your future is
So-
tilted toward, I mean, that's
Yeah.
the kind of terminology that we use. Then your
Yeah.
future is tilted
Right. I mean,
toward the black hole.
I think Janna's book has a really nice description of this,
Thank
if
you,
I may
Priya.
add, Black Hole Blues. And I think Carlo Rovelli recently had a book called In Order of Time. And I think these are the two places where I've seen a very nice, actually lyrical description of what's really happening.
What a beautiful note to end on.
A blues note.
Really lovely to have you both. You're both friends of mine. It's such a pleasure to see you again. Please let's welcome them and thank them for coming. You are free to escape.